And that's why for everyone who wrote this paper, I'd like to formally apologize to you on behalf of Cambridge, because yeah. In this video, we're going to break down the Pure Maths 3 paper from October-November 2023, particularly component 32. I've heard a lot about this paper, including people actually writing a petition to Cambridge to get them to put more favorable thresholds for this paper. Of course, Cambridge didn't oblige, as well as a lot of Reddit comments of people complaining about how difficult this paper was. So I'm very excited to get into it. But before we get into it, subscribe and comment down below which paper would you like to see me break down next. Number 1a, sketch the graph of y equals modulus of 4x minus 2. Okay, to do that we first need to sketch the graph of y equals 4x minus 2, which is a straight line, so we need 2 points. So let's find the point when x is 0. So when x is 0, y is equal to negative 2. So we get the coordinates 0, negative 2. And then let's find the point when x equals 1. So y is equal to 4 times 1 minus 2, y is equal to 2. So we get the point 1, 2. Let's sketch this on a Cartesian plane. This is our x-axis and this is our y-axis. So 1 on the x-axis would be somewhere here, and so 2 on the y-axis would be somewhere there. So that's the point 1, 2. Then we also have the point 0, negative 2, which would be here. And let's draw a line through these 2 points. Like this and like this. So this part, this arm will be y equals 4x minus 2, and the other arm is y equals negative 4x minus 2. And that would be our final answer for this question. Now let's do part B. Solve the inequality 1 plus 3x is less than modulus of 4x minus 2. To do that, we first need to draw the graph of y equals 1 plus 3x. Again, it's a straight line, so we need 2 points. Let's find the point when x is 0. So that's y is equal to 1. That will give us 0, 1. And then when x is equal to 1, that will give us y equals 4. So we have the point 1, 4. 0, 1 is somewhere here. And then we also have the point 1, 4. 1, 4 would be somewhere here. And now we draw a line through our points. And let's just extend our blue graph so that we see the other point of intersection. Okay, so this is our line y equals 1 plus 3x. And you notice that it intersects the blue graph, the modulus graph, at 2 points. First, the line y equals negative 4x minus 2, and secondly, the line y equals 4x minus 2. So let's find the points of intersection by solving the equations simultaneously, and then we should be able to solve our inequality. So for the first point of intersection, we have the lines y equals 1 plus 3x and the line y equals negative 4x minus 2. So let's equate the two equations. Negative 4x minus 2. Let's expand our bracket on the right hand side. That's negative 4x plus 2. Let's put all the terms in x on the left hand side and the other terms on the right hand side. So that 7x is equal to 1, so x is equal to 1 over 7. And so our first point of intersection over here is at 1 over 7, and now we need to find this other point of intersection. So the lines that are intersecting are y is equal to 1 plus 3x and y is equal to 4x minus 2. Let's equate the two equations. Is equal to 4x minus 2. Let's put all the terms containing x on one side and the other terms on the other side. So that's x is equal to 3. And so this means that this point here is x is equal to 3. And our inequality wants us to find the region where 1 plus 3x is less than the modulus graph. In other words, the point where 1 plus 3x is below the blue graph. So we can come to this point at, say, at the point 1, and let's check. Is the red graph below the blue graph? If you check here at x is 1, the red graph is actually above the blue graph. So it means this region in between 1 over 7 and 3 does not satisfy our inequality. We can come and check the region, say this is around -1. At -1, is the red graph is here and the blue graph is here, is the red graph below the blue graph? And yes, the condition actually holds true in this case. So it means one of our solutions should be x is less than 1 over 7. And then we can come and check on this side. For example, at x is, this should be around 3.5. At x is 3.5. We have the red graph here, and it's actually below the blue graph. So this means again we have another solution, x is greater than 3. So our final two solutions for inequality would be, therefore x is less than 1 over 7 and x is greater than 3. Let's move on to our second question. Number 2, the parametric equations of a curve are x is equals to ln t squared and y is equal to e to the power 2 minus t squared for t is greater than 0. Find the gradient of the curve at the point where t equals e, simplifying your answer. Okay, so for parametric equations, let's start by finding dx dt and dy dt. Then we'll make a chain that will help us find dy dx. So dx dt would be, let's bring down our power, that's 2 ln t. If you differentiate ln t, you get 1 over t. And then we've got dy dt. You drop your power, there's 2. We differentiate 2 minus t squared, we get minus 2t e to the power 2 minus t squared. Okay, so let's just simplify dx dt further. Dx dt is equal to 2 over t ln t. So let's make a chain rule for dy dx. dy dx is equal to dy dt multiplied by dt dx. So dy dt in this case is our -2 t e to the power 2 minus t squared multiplied by dt dx. So we have dx dt over here. What we can do to find dt dx is to simply flip the fraction, so the numerator becomes the denominator and vice versa. So this would become t over 2 ln t. Okay, so this means that dy dx is equal to t times t, which is t squared. Don't forget the negative sign over here, times e to the power 2 minus t squared over ln t. And we're told to find the gradient at t is equal to e. So let's substitute t with e. This becomes negative e squared times e to the power 2 minus e squared over ln e. So we can use laws of indices in the numerator, and this becomes negative e is equal to 2 plus 2 minus e squared over ln e. Cancel out the inverse functions, so that becomes 1, and this simplifies to negative e to the power 4 minus e squared, and that's our final answer. Number 3, the polynomial 2x cubed plus ax squared minus 11x plus b is denoted by p of x. It is given that p of x is divisible by 2x minus 1, and that when p of x is divided by x plus 1, the remainder is 12. Okay, if p of x is divisible by 2x minus 1, we can use the factor theorem to say that p of half is equal to 0, and then we can use the remainder theorem to say that p of negative 1 is equal to 12. So let's evaluate p of half using our given polynomial. So that's 2 open bracket half cubed plus a half squared minus 11 half plus b is equal to 0. And so half cubed is 1 over 8, so that's 1 over 8 times 2, which is a quarter, and then plus a quarter a squared, or rather just a, minus 11 over 2 plus b is equal to 0. And then let's simplify our quarter minus 11 over 2, 1 over 4 minus 11 over 2, that's negative 21 over 4. So we've got negative 21 over 4 plus a quarter a plus b is equal to 0. Let's just multiply through by 4 to get rid of the denominator. So that would be negative 21 plus a plus 4b is equal to 0. Now let's evaluate this equation. P of negative 1 is equal to 12. So that's 2 open brackets negative 1 to the power 3 plus a negative 1 squared minus 11 negative 1 plus b is equal to 12. So negative 1 cubed is negative 1 times 2, that's negative 2, plus a plus 11 plus b is equal to 12. And this becomes a plus b, 11 minus 2 is 9, plus 9. Let's bring the 12 to the other side, minus 12 is equal to 0. So we have a plus b minus 3 is equal to 0. Now we have two equations in terms of a and b. We can solve them simultaneously to get the coordinates, rather to get the values of a and b. So let's make a the subject of the formula in the second equation. So that's a is equal to 3 minus b. Let's substitute that into the first equation. Negative 21 plus a is being replaced with 3 minus b plus 4b is equal to 0. So negative 21 plus 3, that's negative 18, minus b plus 4b, that's 3b, is equal to 0. 3b is equal to 18, so b is equal to 6. Now let's evaluate a. A is equal to 3 minus b, so that's 3 minus 6. A is equal to negative 3. And so our final answer would be, therefore, a is equal to negative 3 and b is equal to 6. Let's move on to the next question. Number 4a. On a sketch of an Argand diagram, shade the region whose points represent complex numbers z satisfying the inequalities modulus of z minus 4 minus 3i is less than or equal to 2. and all real values of z are less than or equal to 3. Okay, so we can rewrite the modulus inequality like this. Let's factor out the negative sign here, so that becomes 4 plus 3i is less than or equal to 2. So that means we are drawing a circle with center 4, 3, and its radius is 2. So let's draw our Cartesian plane for the complex numbers. So this would be our real axis, and this would be our imaginary axis. So on the real, we're moving 4 units. Let's say 4 units is somewhere here. On the imaginary axis, we're moving 3 units. So our center would be over here. And now we have to draw a circle with a radius of 2. Of course, in this case, you should probably use your compass to get a perfect circle. So there's our circle. And the second condition is that all real values of z are less than or equal to 3. So on the real axis, 3 is somewhere here. If we draw our line over here, somewhere here. So this region is the region that satisfies both inequalities, and this would be our final answer. Part B. Find the greatest value of argz for points in this region. Okay, so argz is the angle from the positive real axis. Would look something like this. Let me use a different color. So the angle that we are looking for would be this angle. This would be our argz. That would be argz. So to find it, what we can do is we're going to draw these two triangles like this. Draw a line from the center to that tangent, and then a line to the origin. And we can also find, so that will give us, let's highlight that angle that we are going to get from there. So this angle over here, we'll get it from that triangle, and then we need this other angle that's below. I'll highlight it in green. So that's the other angle that we want, this green one, and we get that one from this triangle over here. Okay, so the distance from the center to the tangent over here is the radius, and our radius is 2. So for theta, we have the opposite, which is 2, and we can find our hypotenuse using SOHCAHTOA. So we know that the length from here, this green line over here, to there, that's 4, and the length from here going up is 3. We know that from the coordinates of the center. So we can use Pythagoras to get the line of the third side of that triangle. So a squared plus b squared is equal to c squared. So 4 squared plus 3 squared is equal to c squared. So our c is equal to root 4 squared plus 3 squared. So that should give us c is equal to 5. And so this length over here, the hypotenuse, would be 5. So now we can find theta. We have the opposite and the hypotenuse, which is 5. So that means we're using sine. So we can say that theta in this case is equal to arc sine of our opposite, which is 2 over 5. And then alpha. Let's find alpha. For alpha, let's use our opposite and adjacent. Our opposite is 3, our adjacent is 4. Alpha is equal to arctan of 3 over 4. So theta would be, punch that into your calculator, make sure you're in degrees, arc sine of 2 over 5, 23 point, that's 23.5 Let's just do 5/8. We're going to round off to 1 decimal place. And then alpha is equal to arctan of 3/4, which is 36.87. Right, let's add the two values. We say that argz is alpha plus theta, so argz is equal to 23.58 plus 36.87, and therefore argz is equal to, let's punch that into our calculator, 23.58 plus 36.87. This gives us 60.5 degrees. 0.5 degrees correct to 1 decimal place. Let's move on to the next question. Find the exact value of the integral of x times x plus 1 over x squared plus 4. Okay, this is a very interesting question. And that's why for everyone who wrote this paper, I'd like to formally apologize to you on behalf of Cambridge, because yeah, it's a tricky question. It's not very straightforward and you have to do a lot of work. Usually for questions like this, Cambridge would actually tell you to first find the partial fractions and then integrate. But in this case, you had to figure out that by yourself. That first I have to find the partial fractions and then integrate. And it's also an improper fraction, which is always tricky to find the partial fractions of. But anyways, let's solve it. So let's start by expanding our numerator to x squared plus x over x squared plus 4. The highest power in the denominator is the same as the highest power in the numerator, so it means that we have an improper fraction, and so we have to find the partial fractions of our improper fraction. So the way we're going to do this in this case, I will write the denominator as our numerator for now. That's x squared plus 4 over x squared plus 4. Let me put that in brackets. And we need to get back to our original numerator here, x squared plus x. So now we need to compare the differences between x squared plus x and x squared plus 4. So the x squared is the same. It appears in both cases. In our new numerator, x squared plus 4, we have this 4 that doesn't originally appear in the first numerator. So let's subtract the 4. And we're also missing our plus x, so let's add the x. Okay, and now what we're going to do is we're going to distribute the denominator. So that means everything that's in brackets, we're going to give it its own denominator. So that's x squared plus 4 over x squared plus 4. And everything else, that's the plus minus 4 plus x, we're going to give it its own denominator as well. And so x squared plus 4 over x squared plus 4 will simplify to give us the constant 1. And then we're going to distribute the denominator further over here. So that would become minus 4, give the minus 4 its own denominator, x squared plus 4, and give the x its own denominator, x over x squared plus 4. So only when you've split this into partial fractions can you begin the actual integration. So let's integrate this. That's 1 minus 4 over x squared plus 4 plus x over x squared plus 4. And this is all with respect to x. And our limits are from 0 to 6. Okay. So we've got 1. If you integrate 1, you get x. And for the second one, minus 4 x squared plus 4. If you look in your MF19, we've got, I believe that's 1 over x squared plus a squared, the integral of 1 over x squared plus a squared. That's what we're going to use, and that's what we're going to use to integrate this. So this would become minus 4 over 2. This 4 is the constant over here, and then let's actually rewrite this 4 as 2 squared to make it clear, and that's this 2 is the one that's dividing over here, and that's arctan of, again, 4 over 2. So for x over x squared plus 4, we're going to use the method of recognition to integrate this. So let's just integrate it on the side. What you're going to do is first start by differentiating the denominator. If we differentiate the denominator, we get 2x. And let's put it over our denominator, which is x squared plus 4. But you notice that on our numerator, we only have x. On our original numerator, we have x. So the difference now is that we have a 2. So we're going to multiply by a half to get rid of that 2. So that's half times the integral of 2x over x squared plus 4. If you were to simplify, the half and the 2 would cancel out and give us the x. Now you notice that the numerator is actually just the differential of the denominator. If you differentiate x squared plus 4, you get 2x, which is our numerator. So now we can use the method of recognition, which means that this becomes half ln of the denominator, which is x squared plus 4. And we're going from 0 to 6. Let's just simplify this first. That's x minus 2 arctan of 2 plus half ln x squared plus 4. And let's substitute in the limits. So this would actually become, this is from 0 to 6. So this would be 6 minus, oh my apologies, this should be x over 2. So this bracket over here, I should say x over 2. So 2 arctan of, in this case, x is 6 over 2, plus half ln of 6 squared plus 4. We close our brackets, minus, substitute x with 0, it gives you 0. And then arctan of 0, what's arctan of 0? It's 0. Exactly. So this would also give you a 0. So we'd get half ln of 0 squared, which is 0. So half ln 4 from the 0. Okay, so that's 6 minus 2 arctan of 6 over 2 is 3, plus half ln of 6 squared is 36 plus 4, 40. And then minus the half ln 4, minus half ln 4. So let's use laws of logarithms to simplify. Since they're subtracting, this would become half ln of 40 over 4, which is 6 minus 2 arctan of 3 plus half ln 10. This would be our final answer. This was actually quite a tricky question. I didn't really expect Cambridge to do this, but oh well. Let's move on to the next question. Number 6a, by sketching a suitable pair of graphs, show that the equation cot 2x is equal to 2 minus cos x has one root in the interval 0, x is between 0 and half pi. Okay, so let's draw our plane. We're going from 0 to half pi, and this is 0. So let's start by drawing the graph of y equals cot x. So let's just increase that a bit. It would look something like this, from 0 to half pi. and this is y equals cot x. And now let's draw the graph of y equals 2 minus cos x. So let's put 2 somewhere there. Let's draw a dotted line. And so this would start at 1. Notice that this minus sign means that we are actually going to reflect our graph for cos. So instead of the normal shape like this, we've got the exact opposite, which would be that, but we're only taking from 0 to 90, so it would actually look like this, and this would be y is equal to 2 minus cos x. Okay, and you can tell that we have one root in the interval x is between 0 and half pi. Show, let's move on to part B. Show by calculation that this root lies between 0.6 and 0.8. Okay, so what we're going to do is say f of x is equal to cot x. We're going to move 2 minus cos x. We're coming back to this equation over here, and we're moving 2 minus cos x to the left hand side. So that's now plus cos x minus 2. And let's evaluate f of 0.6. So that's cot x can be written as 1 over tan x. So that's 1 over tan 0.6 plus cos 0.6 minus 2, which gives us f of 0.6 is equal to, and make sure that you're in radians since our interval for this question was given in radians. That's 1 over tan of 0.6 plus cos 0.6 minus 2. That gives us 0.287. And let's evaluate f of 0.8, which is equal to 1 over tan 0.8 plus cos 0.8 minus 2. Let's punch that into our calculator. That's 1 over tan of 0.8 plus cos 0.8 minus 2. We get negative 0.332. Negative 0.332. Okay, and then we have to conclude to get the second mark. Since there is a change in sign, that's this negative sign over here. This is positive and that is negative, so it means we have a change in sign. Since there is a change in sign, a root lies between 0.6 and 0.8, and that's our final answer. Part C. Use the iterative formula xn plus 1 is equals to arctan of 1 over 2 minus cos x n to determine the root correct to 2 decimal places. Give the result of each iteration to 4 decimal places. Okay, let's pick our value for x0. Let's do x0 is 0.6, and so that means x1 is equal to arctan of 1 over 2 minus cos of x0, which is 0.6, and this gives us, ensure that you're still in radians again, so that's arctan of 1 over 2 minus cos 0.6 . That's 0.7053, correct to 4 decimal places, 0.7053. Okay, let's do x2. That's arctan over 1 over 2 minus. Okay, so instead of having to use this value, substituting it here, what we're actually going to do is we're going to use the answer function on your calculator. So that will be cos ans. So you're just going to replace where you had put 0.6 on your calculator, replace it with the answer function on your calculator and press equals, and you get your answer for this iteration. Give it to 4 decimal places, that's 0.6792. And to get the next iteration, don't change anything on your calculator, but simply press equals, and you get 0.6858. Go to the fourth iteration, press equals at 0.6842. Okay, so these ones to 2 decimal places, this would be 0.69. This is 0.68, so we're not yet there. Let's do another iteration. X to the 5. Press equals on your calculator. That's 0.6846, which is approximately 0.68. So we've reached our answer, we found our root, so you can come and conclude that therefore the root is 0.68, and that's our final answer. Number 7. By expressing 3 theta as 2 theta plus theta, prove the identity cos 3 theta is identical to 4 cos cubed theta minus 3 cos theta. Okay, that's a nice identity, yeah? And they've told us to replace 3 theta with 2 theta plus theta. So that means we're actually working from the left hand side to the right hand side. So cos 3 theta has become cos 2 theta plus theta, which means we're using the double angle formula for cos theta. So that would be cos 2 theta cos theta minus sine 2 theta sine theta. And let's use the double angle formula for cos 2 theta. And in this case, we're trying to get to cos cubed. So we'll use the double angle formula that has cos squared in it. So that means that will actually become 2 cos squared theta minus 1 multiplied by cos theta minus sine 2 theta uses double angle formula, that's 2 sine theta cos theta times sine theta. So let's expand our bracket here. That's 2 cos cubed theta minus cos theta minus 2 sine squared theta cos theta. And for sine squared theta, we're actually going to use an identity from AS level, which is that sine squared theta is identical to 1 minus cos squared theta. Remember, we're trying to get an expression that's in terms of cos theta only, so we need to get rid of the sine with cos. So this would become 2 cos cubed theta minus cos theta minus 2. Then we replace our sine squared theta with 1 minus cos squared theta multiplied by cos theta. That's 2 cos cubed theta minus cos theta, and if we expand, that's minus 2 times cos theta times 1, which is minus 2 cos theta, and minus 2 times cos theta times minus cos squared theta give us positive 2 cos cubed theta. And let's add the like terms. 2 cos cubed theta plus 2 cos cubed theta gives us 4 cos cubed theta minus cos theta minus 2 cos theta gives us minus 3 cos theta. And we have therefore proved our identity. Cos 3 theta is identical to 4 cos cubed theta minus 3 cos theta, and that's our final answer. Let's move on to part B. Hence solve the equation cos 3 theta plus cos theta cos 2 theta is equal to cos squared theta. So we know that cos 3 theta from the identity above is equal to 4 cos cubed theta minus 3 cos theta. So we can come here and replace cos 3 theta with that. So it would become 4 cos cubed theta minus 3 cos theta plus cos theta times cos 2 theta is equal to cos squared theta. Let's use the double angle formula for cos to simplify the cos 2 theta. So that's 4 cos cubed theta minus 3 cos theta plus cos theta, and our double angle formula 2 cos squared theta minus 1 is equal to cos squared theta. So that's 4 cos cubed theta minus 3 cos theta plus 2 cos cubed theta minus cos theta is equal to cos squared theta. Okay, let's see if we have any like terms. That's 6 cos cubed theta minus 3 cos theta minus cos theta minus 4 cos theta, and let's bring the cos squared theta to this side, so that's minus cos squared theta is equal to 0. Let's arrange it in order of descending powers of cos minus cos squared theta minus 4 cos theta is equal to 0. You notice that cos theta is actually common in all three terms, so we can factor it out. So it becomes cos theta 6 cos squared theta minus cos theta minus 4 is equal to 0. And let's equate cos theta to 0, and our quadratic, if you hadn't noticed, this is a hidden quadratic. Let's equate that to 0 as well. Minus 4 equals 0. So theta is equal to arc cos of 0. Arc cos of 0 is equal to pi over 2. Let's see what's our in 1 degrees. Oh my. Okay. So this is 180 degrees. Oh. So this would be 90 degrees. And this would serve as our principal value. So PV is equal to 90 degrees. And we need to check if there are any other values within this interval. Let's just sketch a graph of cos x. So this is 90, 180 is over here, that's 180. So when y is 0, that's the line through the x-axis. The only other point would actually be beyond 180, so it means from cos theta equals 0, our only solution is PV is equals to 90 degrees. And now let's solve our hidden quadratic over here. Let's use the quadratic formula because it doesn't look like it can be factorized by sight. So we're going to punch this into the quadratic formula. Your values for a is equal to 6, b is equal to -1, and c is equal to -4. So if we punch that into our quadratic formula, that's -1, so that's 1 plus or minus the square root of 1 squared minus 4a, which is 6, c, which is negative 4, all over 2a, which is 2 times 6. So you get cos theta is equal to, let's punch that into the calculator, 1 plus root 1 squared minus 4 times 6 times negative 4 all over 2 times 6, and we get, that's 1 plus or minus root 97 over 12. Okay, and so that means that we have, let's split this into two equations. So that's cos theta is equal to the positive one, which is 1 plus root 97 over 12, and then the negative one, cos theta is equal to 1 minus root 97 over 12. So for this one, theta would be arc cos of 1 plus root 97 over 12, which would give us theta is equal to arc cos of 1 plus root 97 over 12, and we are in degrees. So that's 25 point, let me just write that down, 25.3014836. Okay, and again we will sketch our graph for cos x, or rather let's just use the one that we have above. So 25.30 would be somewhere over here, right here. And as you can tell, if we keep going with this line, we don't have any other solutions between 0 and 180. So that's the only solution we'll get from cos theta is equal to 1 plus root 97 over 12. Now let's evaluate the negative one. So this would be theta is equal to arc cos of 1 minus root 97 over 12, and that's theta is equal to, plug that into your calculator, make sure you're in degrees, you get 137.51 and so on. Again, let's come to our graph for cos. 137 would be somewhere over here. If you keep moving along this line, you don't have any solutions that are between, any other solutions that are between 0 and 80. So it means that we actually have three solutions for theta here. We can come here and say, therefore, theta is equal to, if we're in degrees, we give our answers correct to 1 decimal place. So that's 25.3 degrees, as over there. If it's exact, you give it exactly as it is. So if theta is 90 degrees, and finally 137.5 degrees, and that's our final answer. Number 8, it is given that 2 plus 3ai over a plus 2i is equal to lambda times 2 minus I, where a and lambda are real constants. Show that 3a squared plus 4a minus 4 is equal to 0. Okay, so let's start by multiplying both sides by the denominator to get rid of the denominator. So that's 2 plus 3a is equal to lambda 2 minus I multiplied by a plus 2i 2 plus 3ai. Let's expand our brackets on the right hand side using FOIL. So that's 2a plus 4i minus ai minus 2i squared. 2 plus 3ai is equal to lambda. Let's simplify the I squared. We know that I squared is equal to 1, so this will become positive 2. Sorry, I squared is equal to negative 1. So it means that negative 2 times I squared is negative 2 times negative 1, which is positive 2. Okay, 2 plus 3ai. Let's expand the lambda. 2a lambda plus 4i lambda minus ai lambda plus 2 lambda. Now let's separate the imaginary and real parts on the right hand side. 3ai, so the real parts are 2a lambda and 2 lambda, and then our imaginary parts, the parts with the I, are 4i lambda minus ai lambda. So let's equate our real part on the left hand side to the real part on the right hand side. So 2 is equal to 2a lambda plus 2 lambda. Now equate the imaginary part on the left to the imaginary part on the right. So that's 3ai is equal to 4i lambda minus ai lambda. Let's factor out our lambda here. So that's 2 is equal to lambda 2a plus 2. And okay, before we do that, what we can actually do is, you notice that in this equation we can easily get rid of the I by dividing both sides by I. So this would become 3a is equal to 4 lambda minus a lambda. And so that actually means we have two equations in terms of a and lambda. So we can then solve those two equations simultaneously to end up with the requested equation. So let's make lambda the subject of the formula in our first equation. Lambda is equals to 2 over 2a plus 2. Let's substitute that into the second equation. So that's 3a is equal to 4 times 2 over 2a plus 2 minus a times 2 over 2a plus 2. That's 3a is equal to 8 over 2a plus 2 minus 2a over 2a plus 2. Multiply both sides by 2a plus 2 to get rid of the denominator. So that's 3a times 2a plus 2 is equal to 8 minus 2a. 3a times 2a is 6a squared. 3a times 2 is 6a is equal to 8 minus 2a. Let's move all the terms to the left hand side. 6a squared plus 6a plus 2a minus 8 is equal to 0. You get 6a squared plus 8a minus 8 equals 0. And remember, so let's divide the whole equation by 2. That will give us 3a squared plus 4a minus 4 is equal to 0, which is what they are looking for. And we have proved their requested equation. Part B, hence find the possible values of a and the corresponding values of lambda. So that means we have to solve the quadratic in terms of a. That's 3a squared plus 4a minus 4 is equal to 0. So let's factorize this. That's 3a minus 2 and a plus 2 is equals to 0. And so this means that a would be 2/3 over here and a would be -2. Now we had an equation in terms of a and lambda that we can use to evaluate lambda. In part A, this is our equation. Lambda is equals to 2 over 2a plus 2. Let's use that to get lambda. Lambda is equals to 2 over 2a plus 2. So when a is 2/3, lambda is equals to 2 over 2 times 2 over 3 plus 2. Lambda is equal to, punch that into your calculator, that's 2 over 2 times 2 over 3 plus 2, 3/5. So lambda is equal to 3 over 5. And then when a is equal to -2, that's 2 over 2 times -2 plus 2. Lambda is equal to, our denominator would be -4 plus 2, which is -2. So that's lambda is equal to 2 over -2, which is -1. So that means our final answer would be a is equal to 2/3, which leads to lambda is equal to 3/5, and a is equal to -2, which leads to lambda is equal to -1. Let's move on to our next question. Oh, that's a pretty diagram. The diagram shows the curve y equals sin x cos 2x for x is between 0 and pi and a maximum point m, where x equals a. The shaded region between the curve and the x-axis is denoted by r. Part A, find the value of a correct to 2 decimal places. So a is the x coordinate at m, and m is a maximum point, which is a stationary point. So it means we have to find dy dx and then equate dy dx to 0, and so for x. So let's find dy dx. So dy dx, in this case we have two functions multiplying each other, so we're going to use the product rule, which states that dy dx would be equal to u dv dx plus v du dx. So let's do that. Let's start by, so let's do sin x times, if you differentiate cos 2x, you get -2 sin 2x plus cos 2x. If you differentiate sin x, you get cos x. Okay, so dy dx is equal to -2 sin 2x sin x plus cos 2x cos x. And let's expand sin 2x and cos 2x using double angle formulae. So -2, that's 2 sin x cos x sin x plus, in this case you notice that when we finally completely simplify the left part here, we'll end up with an expression in terms of sin squared x cos x. So in this case it means when we expand cos 2x, we need to expand using our formula that will give us something in terms of sin squared x, because we already have the cos x part. So that means the double angle formula we're going to use is cos 2x is equal to 1 minus 2 sin squared x. So that's 1 minus 2 sin squared x times cos x. Let's expand, that's minus 4 sin squared x cos x plus cos x minus 2 sin squared x cos x. And let's simplify our like terms. That's -6 sin squared x cos x plus cos x, and this is dy dx. And remember that we're looking for the x value, the x coordinate at a stationary point, so we're going to equate this to 0. So that's -6 sin squared x cos x plus cos x is equal to 0. Let's factor out cos x open bracket minus 6 sin squared x plus 1 is equal to 0. So that means we have cos x is equal to 0, and we have negative 6 sine squared x plus 1 is equal to 0. What's our interval? X is between 0 and pi. Okay, so x is equal to arc cos of 0, which is pi over 2. And the next solution, if we are to draw our graph for cos x, we have pi over 2 here. The next solution, as you can tell, which is 3 pi over 2, is already outside of our given interval of 0 to pi. So that's our only solution from here. But if you come to the graph, you notice that pi over 2 would be somewhere here. So pi over 2 is the x value at this stationary point, but we want that stationary point, so let's evaluate our other trig equation. So this becomes 6 sine squared x is equal to 1 sine squared x is equal to 1 over 6. Sine x is equal to, take the square root of both sides, so you get plus or minus root 1 over 6, and here you get x is equal to arcsine of plus or minus root 1 over 6. So we get x is equal to arcsine of, let's start with a positive 1 root 1 over 6, and we are in radians, 0.421 or 0.421. Okay, and the other one would be x is equal to negative root 1 over 6, and that will give us negative 0.421. So let's go back to our diagram and find our correct solution. Okay, so 0.421 would be somewhere here. That would be 0.421. So that would be our x value and our value for a. So they want their answer correct to 2 decimal places. So it means that therefore a is equal to 0.42. Let's move on to part B. Find the exact area of the shaded region R, giving your answer in simplified form. Okay, so R is that shaded region, and to find the area under a curve we use integration, and so it means we're integrating y equals sine x cos 2x, but we need to find the limits, which are these 2 points over here. And what we can do is to equate our function to 0, so sine x cos 2x is equal to 0, so that becomes sine x is equal to 0 and cos 2x is equal to 0. Here you'd get x is equal to arcsine of 0, which is going to give us 0, and and if we sketch the graph for sine, if we can sketch it over here, we've got 0 over here, pi, and 2 pi. So the other time it intersects 0 would be at pi, so that's this point 0 and pi. Those are those 2 points. We don't want those points, so let's evaluate cos 2x rather. So 2x is equal to arc cos of 0. You get 2x is equal to pi over 2, and x would be pi over 4, and pi over 4 is actually this point over here, and we can find this other point by simply saying pi minus pi over 4. So this should be 3 over 4 pi. So those are our two limits. And we are integrating our function sine x cos 2x to find the area of the shaded region. So it's the integral of sine x cos 2x with respect to x from pi over 4 to 3 over 4 pi. Okay, so these are two functions that are multiplying each other, so we're going to use integration by parts. Let u equals sine x and dv dx equal cos 2x. If you differentiate u, you get du dx is equal to cos x. If you integrate dv, you get v is equal to half sine 2x. And now let's use our formula for integration by parts. So this would be the integral of sine x cos 2x dx is equal to uv, which is half sine 2x sine x, minus the integral of, let's put the half outside, v du, half sine 2x cos x with respect to x. So we need to integrate this sine 2x cos x. So the integral of sine 2x cos x with respect to x. So u in this case will make it cos x, and dv will be sine 2x. So du dx is equal to negative sine x, and v is equal to, that would give us half cos 2x, and it will be negative. So if we use the formula for integration by parts, this will be the integral of sine 2x cos x dx is equal to uv, which is minus half cos 2x cos x minus v du, so that's minus half. So there's a minus here, there's a minus here, and we're also going to have a minus here, so it means that overall it will be a minus sign, and that's sine x cos 2x dx. Okay, so that means we're going to take this and we're going to come put it here. So that would become the integral. Okay, we're going to run out of space here. So that's the integral of sine x, we're over here, sine x cos 2x dx is equal to half sine 2x sine x minus half, and then we said we're replacing this with this integral over here. That's open bracket minus half cos 2x cos x minus half the integral of sine x cos 2x dx. And let's expand that out. So that's the integral of sine x cos 2x dx is equal to 1 over 2 sine 2x sine x plus minus half times minus half gives us a quarter. That's cos 2x cos x plus a quarter, the integral of sine x cos 2x. If you're not careful, you keep going around in circles and you'll be integrating and you'll be going no. But what I want you to notice is that this is exactly the same as what you have on the left hand side, so we can actually group like terms. So this becomes the integral of sine x cos 2x dx minus 1 over 4 the integral of sine x cos 2x dx, which is equal to half sine 2x sine x plus a quarter cos 2x cos x. So on the left hand side, that's 1 minus a quarter, so that's 3 over 4 the integral of sine x cos 2x dx is equal to half sine 2x sine x plus a quarter cos 2x cos x, and then let's divide both sides by 3 over 4, so that will become the integral of sine x cos 2x dx is equal to, this would be 2 over 3, so it would be 2 over 3 sine 2x sine x, and this would be 1 over 3 cos 2x cos x. And remember that our limits were actually pi over 4 and 3/4 pi. So that means we are now at the stage 2/3 sine 2x sine x plus a third cos 2x cos x, from pi over 4 to 3 over 4 pi. We don't have any space below, so I'm just gonna erase above so we can finish off this question. Okay, so now we substitute in our limits, so that would be 2 over 3 sine 2 times 3/4 pi, so we can write that as 6 over 4 pi sine 3/4 pi plus 1 over 3 cos 2 times 3/4 pi, that's 6 over 4 pi cos 3/4 pi, and then we're going to subtract 2/3 sine 2 pi over 4 times sine pi over 4 plus a third cos 2 pi over 4 cos pi over 4. And then we'll punch this into our calculator. So let's do the first bracket. That's 2 over 3 sine 6 over 4 pi, make sure you're in radians as well, sine 3 over 4 pi plus 1 over 3 cos 6 over 4 pi cos 3 over 4 pi, and that gives us negative root 2 over 3. So the first bracket is negative root 2 over 3, and then we're subtracting the second bracket. So that's 2/3 sine of 2 pi over 4 times sine pi over 4 plus 1/3 cos 2 pi over 4 times cos pi over 4. That gives us root 2 over 3. Root 2 over 3. So this simplifies to give negative 2 root 2 over 3. And this is our area. The only reason it's negative is that the area lies below the x-axis. If you check, the shaded region is below the x-axis, so you're always going to get a negative answer. But we know that area is never negative, so you give your final answer as a positive value. So that's 2 root 2 over 3 as our final answer. Let's move on to the next question. Okay, number 10. The equations of the lines L and M are given by L is R is equal to 3, negative 2, 1 plus lambda 1, 1, 2, and M is R is equal to 6, negative 3, 6 plus mu negative 2, 4, 6, where C is a positive constant. It is given that the angle between L and M is 60 degrees. So this means that cos 60 degrees is equal to L dot M, the dot product of L and M, and the product of their magnitudes. So let's start by finding their dot product. So we're going to use the direction factor. So it's the dot product of the direction factors. Negative 2 for C. So 1 times negative 2 is negative 2, 1 times 4 is 4, and 2 times C is 2C, which simplifies to 2 plus 2C. And then the magnitude of the direction vector of L is equal to root 1 squared plus 1 squared plus 2 squared, which is equal to root 6. And the magnitude for M is equal to square root of negative 2 squared plus 4 squared plus C squared is equal to, that will be root 20 plus C squared. So that's cos 60 is equal to, our dot product is 2 plus 2C over root 6 times root 20 plus C squared. So punch cos 60 into your calculator, make sure that you're in degrees. So cos 60 is equal to a half. So we've got 1 over 2 is equal to 2 plus 2C. We can write our denominator as root 6 times 20 plus C squared. Okay, now let's square both sides to get rid of the square root sign in the denominator. So that would be half squared is equal to 2 plus 2C squared over, this would now become 6 times 20 plus C squared. And so this is a quarter. And if we expand our numerator, that's 4C squared plus 8C plus 4 over 6 times 20, that's 120 plus 6C squared. Let's get rid of the denominator, so that's a quarter times 120 plus 6C squared is equal to 4C squared plus 8C plus 4. Multiply both sides by 4 to get rid of the quarter, so that's 120 plus 6C squared is equal to 16C squared plus 32C plus 16. Put all the terms on one side, 16C squared minus 6C squared plus 32C minus 120 plus 16 is equal to 0. This is 10c squared plus 32c minus 104 is equal to 0. Let's divide the whole equation by 2, so that's 5c squared plus 16c minus 52 is equal to 0. And now let's factorize. So that's 5c c. Okay, so this will be 2, and then this will be 26. This is minus positive, so let's just check that's correct. 5c times negative 2 gives us negative 10c, then 26c minus 10c gives us 16. If you multiply these two numbers, 26 and negative 2, you get negative 54. Okay, so c is either equal to negative 26 over 5 or c is equal to 2. And what were we told in the question to determine what c is? We were told that c is a positive constant. So it means that our final answer would be, therefore c is equal to 2. Let's move on to part B. Show that the length of the perpendicular from 6, negative 3, 6 to L is root 11. Okay, so let's draw a diagram of what this would look like. So this is our line L, and this would be, let's call this point F. That's the 6, negative 3, 6. And then there's this point where our vector from F crossing the line L intersect. So let's call that point X. And what we want is the length of this perpendicular fx. So we want the length modulus of fx. That's what we want. So let's find, we know that x lies on the line L, so we can find the general coordinates of x using the equation of line L. So line L and the equation R is equal to 3, negative 2, 1 plus lambda 1, 1, 2. And so this means that the general coordinates for our vector OX would be 3 plus lambda times 1. So that's 3 plus lambda, negative 2 plus lambda times 1, negative 2 plus lambda, 1 plus lambda times 2. So that's 1 plus 2 lambda. Those are our general coordinates. Now we need to find the displacement vector fx. So fx is equal to OX minus OF. So OX is 3 plus lambda minus 2 plus lambda, 1 plus 2 lambda, minus 6, negative 3, 6. And this gives us 3 minus 6 is minus 3 plus lambda, negative 2 minus minus 3, that's 3 minus 2, so that's 1 plus lambda, and then 1 minus 6 minus 5 plus 2 lambda, that's fx. So if two lines or if two vectors are perpendicular to each other, it means that their dot product is equal to 0. And so that's the idea we're going to use to evaluate lambda, because we can't just find the modulus of fx right now since we have lambda. So first let's find lambda by using the idea that the dot product of perpendicular lines is equal to 0. So that means that negative 3 plus lambda, 1 plus lambda minus 5 plus 2 lambda dot, we use the direction vector for L, so that's 1, 1, 2, and we're saying this is equal to 0. So negative 3 plus lambda times 1 will remain the same, plus 1 plus lambda times 1, so that will remain the same, plus negative 5 plus 2 lambda times 2 is equal to 0. So that's negative 3 plus lambda plus 1 plus lambda. This is minus 10 plus 4 lambda is equal to 0. So minus 3 plus 1, that's minus 2, minus 10, minus 12. And then lambda plus 4 lambda, that's 6 lambda, is equal to 0. So you get 6 lambda is equal to 12. You get lambda is equal to 2. And now that we have lambda, we can now find the exact coordinates of fx. So if x is negative 3 plus lambda, 1 plus lambda, negative 5 plus 2 lambda, and we will substitute lambda with 2. So this becomes negative 3 plus 2, 1 plus 2, negative 5 plus 2 times 2, and this simplifies to give negative 1, 3, negative 1. Now let's find the magnitude of fx, which is equal to the square root of negative 1 squared plus 3 squared plus negative 1 squared. So that means that the length of fx is equal to 1 plus 9 plus 11, plus 1, so that's all root 11. Now let's move on to number 11. The variables x and y satisfy the differential equation x squared dy dx plus y squared plus y equals 0. It is given that x equals 1 when y equals 1. Solve the dE to obtain an expression for y in terms of x. Okay, let's start by moving all the terms with y to the right hand side. So this becomes negative y squared negative y. And now we're going to do separation of variables, so that would be 1 over negative y squared negative y is equal to 1 over x squared. This is dy and that's dx. Let's factor out the negative sign in the denominator and bring it up to the fraction line, so that becomes y squared plus y is equal to, let's bring out the x squared using laws of indices. Okay, and now we'd have to integrate both sides, but the catch here is that you can't just integrate this fraction. First you'd have to do partial fractions before you start the integration. So let's do partial fractions for that. That's negative 1 over y squared plus y. We can actually factor out a y in the denominator, so it becomes y open brackets y plus 1 is equal to, this is a over y plus b over y plus 1, and so this becomes negative 1 is equal to a times y plus 1 plus by. Let's find a. So at y equals 0, negative 1 is equals to a open bracket 0 plus 1, and this becomes a is equal to negative 1. And then to find b, we'll say at y equals negative 1. So this becomes negative 1 is equal to b times negative 1, and you get negative 1 equals negative b, so b is equal to 1. So this means that our partial fractions are negative 1 over y squared plus y is equal to negative 1 over y plus 1 over y plus 1. Now we can actually integrate. So it becomes the integral of negative 1 over y plus 1 over y plus 1 with respect to y is equal to the integral of x to the power negative 2 with respect to x. If you integrate negative 1 over y, you get negative ln y, and then 1 over y plus 1 is ln y plus 1 plus a constant is equal to, that would become negative x to the power negative 1. And let's use laws of logarithms to simplify that. This would become ln y plus 1 over y plus c is equal to negative 1 over x. And we were told that we have the points 1, 1. We can use these now to evaluate c. So this would become ln 1 plus 1 over 1 plus c is equal to negative 1 over x. So that's ln 2 plus, this would be over 1 rather. So that's ln 2 plus c is equal to negative 1. So c is equal to negative 1, negative ln 2. Now let's substitute it back here. So that's ln y plus 1 over y minus 1 minus ln 2 is equal to minus 1 over x. Now we have to make y the subject of the formula. So this becomes ln y plus 1 over y is equal to 1 plus ln 2 minus 1 over x. And let's use the exponential function to get rid of ln here. So this becomes y plus 1 over y is equal to the exponential of 1 plus ln 2 minus 1 over x. Using laws of indices, we can rewrite this as e to the power 1 times e to the power ln 2 times e to the power negative 1 over x, which gives us y plus 1 over y is equal to e, the e and the ln will cancel out here, so it will be times 2 times e to the power negative 1 over x. So that's y plus 1 over y is equal to 2e. And now let's use laws of indices to add these two powers together. That's 1 minus 1 over x. And here we can distribute the denominator y so that we simplify. So we have y over y, which gives us 1. Then we have 1 over y is equal to 2e to the power 1 minus 1 over x. And if we move the 1 to the other side, it becomes 1 over y is equal to 2e to the power 1 minus 1 over x minus 1. And then that would therefore give us our final answer. Y is equal to 1 over 2e to the power 1 minus 1 over x minus 1. That would be your final answer. Part B. State what happens to the value of y as x tends to infinity. Give your answer in an exact form. So if you look at our denominator here, in the denominator we have 2e to the power 1 minus 1 over x minus 1. If you replace x with infinity, we end up with 1 over infinity. And 1 over infinity is assigned a value of 0. So that will mean you end up with basically 2e to the power 1 minus 0 minus 1 in the denominator, which is 2e to the power 1 minus 1. So it means that as x tends to infinity, y approaches 1 over 2e minus 1. And I think that's the final question. We are done for this paper. If you enjoyed this breakdown, comment down below which paper you'd like me to break down next, and also subscribe for more videos like this. Thank you for watching.